Here's how on Radiata.ai you can run classification models with brain structural MRIs on the fly. Classifiers are a core tool in data science. On Radiata, you can use classifiers to discover the optimal set of brain imaging features for predicting clinical diagnosis or any other variable of interest. We've made classification modeling very interactive, so you can get an intuition for how your model is treating different individual subjects and brain features. Here I'll show you how you can set up a classification model to predict an individual's clinical diagnosis of Alzheimer's disease or cognitively normal. So in the modeling panel, for the model type, I choose classification. For the response variable, I'm going to use clinical diagnosis. And for the predictors or the brain imaging features, I'm going to use the gray matter volume in all cortical and subcortical brain regions. So that's how you specify this here. I've split the data so that 75% of the scans are in the training data set and 25% are in the testing data set. Once that's all set, I just click here to run the model. And under the hood, this will use a linear discriminant analysis classification model in scikit-learn. Now that the model is run, we can check out the results. We can see here that the accuracy was pretty good, 95.4% in the test data set. Now we can use a few essential tools to dive into this model. So the confusion matrices are shown here for the training and the test data sets. And so here, this row is the true AD cases, and we can see that 100 of them were correctly predicted, but 37 were incorrectly predicted as cognitively normal. This matrix is interactive, so I can click this cell and show those 37 cases in the brain structure latent space. And do the same for the correctly predicted 100 cases and see if there's any systematic differences and where the different cases fall in this space. You can also use the latent space to overlay different scores. So here I have the predicted probability of Alzheimer's disease. And so you can look at different groups like the high probability predicted cases versus the low probability predicted cases to see how the prediction probability forms a spectrum across the latent space. Here you can use the ROC curve to understand the classification model performance at different thresholds. So I've highlighted the AD cases here, and we can move along this curve, and at each point or at each threshold cutoff, we can see the ratio of true positives to false negatives, for example, the sensitivity and the specificity in the area under the curve. And we can also click here, which will show each of the different classes in the latent space. So we can see if there's any systematic differences in where the false positives and false negatives are falling. Next, we can examine the feature weights for this classification model to see which brain features were most important. This is a key step for validating that your model makes biological sense. Here we show the feature weights both as a heat map and also as a brain map in the brain viewer. You can threshold this map to verify that regions we know are vulnerable in Alzheimer's, like the hippocampus, are making the strongest contributions to the predicted diagnosis. And then, for example, you can look at the misdiagnosed cases, and if you click one of those scans in the latent space here, you can bring up their T1 scan and begin to understand which features in their brain led to that misdiagnosis. This can be helpful for patient stratification. Finally, you can compare two classification models. So here I ran a new model using brain structure embeddings as the predictors, and you can compare the accuracy for this model to the previous model that we ran using the region gray matter volumes. You can see, for example, that the embeddings model does slightly better in predicting Alzheimer's cases. When we look at the embeddings-based feature map, we can see that it highlights some of the same regions like the hippocampus, but it's also sensitive to new features like the shape around the ventricles. So this is an overview of how you can build classification models on Radiata.ai and explore the results in a highly interactive way.